Hey everyone, let's look at implicit differentiation, an implication of the chain rule. This is an application of the chain rule, so it is very important that you know the chain rule. Just to recall, the chain rule does state the derivative of f of g of x equals f prime of g of x times g prime of x. Okay, just a quick reminder for how this works. Let's take this derivative. Now remember, y really equals sine of the square root of x to the fourth plus 23x quantity to the fifth. I know it's written this way, but remember that x to the fifth is the outermost function. So the derivative is going to be 5, keep the inside the same, to the fourth, times the derivative of the inside, right? Just take the derivative of the sine part, leave the inside the same, times the derivative of the square root guy, leave the inside the same, times the derivative of the inside. All right, and so there we go. That's our derivative. So just to point out, we use the chain rule once, twice, 3 times, 4 times, depending on how you look at it, right? But I would say we used it 3 times. So just remember, you can iterate the chain rule, and while it's complicated, it doesn't make the problem all that much more difficult. Or doesn't make the problem all that much more lengthy, I guess I should say. Anyway, I claim that there's an application that we can use of the chain rule, and just stick with me for a moment. We've always thought of functions in the term y equals f of x, find dy over dx, find f prime of x, but there do exist functions where you could write them like this, right? Sine of x plus y equals y squared cosine of x, right? It still involves x's and y's, but it's not as simple as y equals blah. And if you look at a function like this, I think you could pretty clearly see you can't solve for y in this sort of situation. And yet, you still can graph this curve. In fact, if we get out Desmos, you go to desmos.com if you'd like to do this. But if we go ahead and just type in this equation, right here, and we just type in sine of x plus y equals y squared cosine of x, you can get a function, right? And if you want to go ahead and experiment with this, then feel free, you know, kind of get some weird stuff like that. Let's see if we did like a 3x or something. You can get some really wacky stuff going on here, right? You know, just, and if you want to just take a second, you know, fool around and see what you get, you can feel free, right? But anyway, the point is, we have these graphs, we have these curves, and while they definitely don't satisfy the vertical line test, so to speak, you couldn't write this as y equals, you can still examine their graphs and analyze their graphs the same way that you normally would and talk about the slope of the tangent line of the function at any given point. And in fact, it still works out to be dy over dx, like the same way. Now, the way that we actually differentiate is a little bit different, and that's why I keep mentioning the chain rule. Okay? So if I say something like find dy over dx for y satisfying this equation, what I really mean is find a function that will give you the slope of the tangent line to this curve, or this graph, at any point x comma y. So here's how we do it. Now this is going to be a little bit of a lengthy process, even lengthier than the chain rule. However, it is very formulaic, and you will be doing the same process every time. And this is where your differentiation skills are going to need to be really sharp. So what we're going to do is we first implicitly differentiate. Which means take the derivative of both sides. both sides of the equation, that is. Okay, so what's the derivative of the left side? Now, if you notice, x plus y is its own function, so we're going to take the derivative of sine, and we leave the inside the same. Now, we're going to treat y as a function of x. So the derivative of x with respect to x is 1. The derivative of y with respect to x is not 1, it's not 0, it is dy over dx. So whenever I ask you to differentiate y, you write dy over dx. So now, y squared, again, that's just some function of x. So we're going to take its derivative. Now, believe it or not, that's actually a chain rule. So if you pretended that y were like sine of x or square root of x or something, I said, find the derivative of that. Well, you would do, okay, it's going to be 2, right, because x squared is the outer function, y is the inner function. Leave the inside the same, times the derivative of the inside, y, which remember is dy over dx. Right. Just to point out, right, derivative of y, dy over dx. Derivative of y, dy over dx. Okay? And anyway, this is a product rule, so we're going to leave cosine the same. Leave that whole thing the same. Plus, and this is a little bit nicer, this is going to be y squared times, now we just take the derivative of the cosine part, and we get that. The calculus is done at this point. The differentiation is done. Now all we need to do is simplify, and that it can take a little bit of work. I gave a really nasty problem. So what I'm going to do is I'm going to distribute the cosine of x plus y to the 1 and to the dy over dx. Going to put the minus sign out here, maybe. And that's what I'm going to do. Okay. So this implies that we have cosine of x plus y times 1, really, plus cosine of x plus y times dy over dx, and then this equals 2y. I'll put the cosine x in front so I can put the dy over dx at the end, minus, it doesn't really matter which way you put this, y squared sine of x, okay? Next up, right, so here what we did was we simplified. Next, what we're going to do is we want to get all of the dy over dx terms on one side of the equation and all the non-dy over dx terms on the other. So I'll just say combine dy over dx terms. Okay? And so this is going to give us cosine of x plus y dy over dx minus 2y cosine of x dy over dx. Okay? You see, I just took, well, maybe I'll use like black or something. I took these two terms and put them on the same side of the equation. I mean, actually, no, I'll do this. I'll use a highlighter. Right? I had this, and I had this, and now I put them both on the same side of the equation, and everything else can go to the other side. This is going to be minus, no, we're not using black, we're using blue, okay. Minus cosine of x plus y minus y squared sine of x. Okay? And at this point, we're almost done. We're just going to solve for dy over dx. And so the way we do that is we just factor out the dy over dx and then divide. So we get cosine of x plus y minus 2y cosine of x times dy over dx. And then this equals, you know what, I'm feeling lazy. Right there. And then we just divide by the left-hand side, the non dy over dx part. Right, so like right here. Okay? And so, right, once we divide out by something, we just cross it out. Right? And so it goes away. And that's our solution. That's our answer. Dy over dx equals this complicated nonsense. Okay? Now, once again, the process of differentiating both sides of an equation is called implicit differentiation. Okay, implicit differentiation. Okay, now note that the chain rule is extremely important. When do we use the chain rule? Well, anytime we had a composition of functions, of course, right? But also anytime that we did anything with y, right? Anytime we had to take the derivative of y squared, or, just sine of y, we're using the chain rule because we think of y as a function of x. So it's very important that you be used to the chain rule and be able to spot when you need to use the chain rule. Okay. Also, just throwing this out there because sometimes students see this in a textbook or they just have seen it in another class. Y prime is another way of writing dy over dx. I'll typically write dy over dx, but just to let you know, if you ever see that in implicit differentiation, that's why. All right, so let's take another look. Let's take a look at another example, right? Find the equation of the tangent line to this curve at the point 2, comma, negative 11. Now, make sure that that's legit. I'm not quite sure that negative 11... No, I think it's okay. It's okay. Let's maybe, instead of... Is 2 negative 11 actually a point on the curve? If x equals 2. I don't think that quite works. Hold on a sec. We have 4 plus 4y minus y squared equals 4. I think... Oh, no, that's right. I think this does work. I just need to change what this number winds up being. This is 4 minus 22 minus 121. Yeah, this shouldn't be 4 here. Sorry, right, guys? This should be negative 143. Negative 139. Now I think it works. Okay, sorry about that. Little mistake there. Right, anyway, so we're just going to implicitly differentiate, right? So differentiate both sides, and you get 2x, right, the derivative of x squared. Just to be crystal clear, we're getting this. And then the derivative of this guy, and then the derivative of that guy, and then the derivative of this negative 139, which we should know is 0, okay? So anyway, what's the derivative of x? Y. Well, we take the derivative of x, we get y, plus x times the derivative of y, which is dy over dx, minus 2y dy over dx, right? See how we got our derivatives here? This whole thing in green was the derivative of that guy. And then this right here, we differentiate it, and we get this guy. Okay? So, anyway, just want to finish things off. The derivative of any constant is 0. So, like that. And now at this point, we just want to, again, simplify if necessary, get the dy over dx terms on one side, get all the other terms on the other, factor it out, and solve. So at this point, we're going to have x dy over dx minus 2y dy over dx equals negative 2x negative y. Okay? And at this point, we just factor out our dy over dx term. And then just divide by the non-dy over dx terms on the left side. And that's our answer, right? dy over dx equals negative 2x minus y over x minus 2y. Now, just to clarify, this isn't the answer to the question. It says find the equation of the tangent line at the point 2, comma, negative 11. So, at this point, we draw a vertical line right there, and we write 2, comma, negative 11. Okay? And we just plug in our numbers, right? And so then this gives us negative 2 times 2 minus negative 11 all over 2 minus 2 times negative 11. And when you simplify this out, I think you get, what is that? Negative 4 plus 11, I think it's negative 7 divided by 24. Okay? So you say, okay, well, then that's the right answer, right? Well, no, we have to find the equation, okay? Right? So we'll say, so the equation of the tangent line at to negative 11 is, and remember, it's y minus y1 equals the slope, which we just found to be negative 7/24, times x minus x1. Or y plus 11 equals negative 7/24 times x minus 2. Okay? So that's how we get it. Okay? One more example, right? Just to see how quickly we can do this guy. Implicitly differentiate. Take the derivative of the outside, leave the inside the same. And here we actually have a product rule. And then this is going to equal 1 goes away. We get, positive cosine of y times dy over dx. Because, again, we're using the chain rule. And so if we distribute the negative sign, we get negative y sine of xy. Well, I guess that's also a negative x sine of xy dy over dx equals cosine of y dy over dx. You could add the x sine of xy dy over dx over the other side. Totally fine. In fact, let's do that. Equals x sine of xy dy over dx plus cosine of y dy over dx. And then when you factor out the dy over dx and divide, you will get this. Negative y sine of xy all over this lovely stuff. All right, so we have that. One more example. And this is a nice little, it's not from this textbook, but it's a nice little application to biology. Models to predict the fraction of a population will be infected into disease. Kermack-McKendrick model, we get this stuff right here. And they define A, Q, and rho. That's not a P, it's rho. Okay, how do the outbreak size, or I should say, the outbreak size A change with an increase in transmissibility Q? Right, so here what they're saying is find dA over dQ, right? So I guess we're assuming that rho is a constant, E is the number. But we need to know, right, we're treating Q as though it's X, right? So think of Q as though it's X. Think of A as though it's Y, right? So anyway, let's see what we've got here. If we implicitly differentiate, then we get rho times the derivative of e to the negative qa, which is e to the negative qa times, now just be a little careful, right, because both q and a are variables here. So we have to do a product rule. We're going to get negative 1 times a minus q times dA over dQ equals, okay, the derivative of 1 is just 0, and then this is negative dA over dQ. And then we're going to have, when we simplify this out, we're going to get negative rho A e to the negative QA minus rho Q e to the negative QA dA over dQ equals negative dA over dQ. And then we do the same thing, right? We group the dA over dQ terms together. And so we're going to wind up and get this guy on the other side. So we're going to wind up getting dA over dQ, right? We're adding the right side over, minus PQ, well, that's a PQ, oh my gosh, e to the negative QA dA over dQ, it's a Q, promise, equals rho A e to the negative QA, yeah, right, just to be clear, because it can be tough to keep track of all these terms, right, this guy went here, this guy stayed put, and this guy came over here, but we added it over, right, so you see how the signs switched, right, and so anyway, you just factor out that dA over dQ, divide, and you wind up getting that this equals rho A e to the negative QA all over 1 minus, right, because you divide out by this, becomes 1 minus rho Q e to the negative QA, and that's it. And we're done.